Hi guys, welcome to today's lecture covering pH scales and buffers. Fun. Alright, so last time we talked about acids and bases and their characteristics and properties and definitions with the Bronsted-Lowry versus the Arrhenius definitions and different examples. Today we're going to talk about strong acids and bases versus weak acids and bases. And so acids and bases can be categorized as strong or weak depending on how much they ionize or dissociate in aqueous solution. So strong acids are going to completely ionize in solution. That means they're going to completely break apart to make an H3O or hydronium ion to make it more acidic. So some good examples of strong acids: hydrochloric acid. All right, I see here bromic acid, iodic acid, nitric acid, chloric acid, and sulfuric acid. Okay, those are ones that completely ionize in solution. They're going to completely break apart into ions. All right, and there's basically going to be no intact acid molecules anymore. So, like for example, if this was HCl that we put into water, all of these are going to be, H plus ions and Cl ions. Okay, there's not going to be any intact HCl molecules left over. All right, so that's what this equation right here is representing. That HCl, when you add it to H2O, is going to completely ionize to make the hydronium ion, H3O plus. Okay, remember we can always interchange that as just saying H plus. And chlorine ions. This single arrow right here, okay, when you see a single arrow, it indicates complete ionization, that there's no intact HCl left over when this is all dissolved. We're going to see this is going to be different than a double arrow, which we'll see in a couple of slides. All right, so strong acids are also strong electrolytes. They're solutions that can conduct electricity, and because well, they ionize into positive and negative ions, and positive and negative ions are able to conduct electricity, are able to transfer electrons very easily between themselves to conduct electricity, complete a circuit and conduct electricity. So we can see down here in the bottom picture that this solution on the very left, okay, is not an electrolyte at all. It doesn't conduct electricity at all, okay, because it doesn't light up that light bulb. The middle one we can say is probably a weak conductor because it lights it up a little bit. And last but not least, that one on the very right is probably, a strong acid or a strong electrolyte because it lights up that light bulb very brightly. All right, so strong acids are strong electrolytes. Now, acids can be classified also as monoprotic acids or diprotic acids, just depending on how many protons or how many H plus molecules, okay, H's that they have in their compound can be ionizable or removed in a sense. So all of these guys here are what we call monoprotic acids. They have one ionizable proton, so one proton that's going to come off in solution. And so we can see that it's always written as the front. Okay, the front one is the one that actually gets ionized. Diprotic acids, di means two, so they have two ionizable protons. Okay, and we can see in H2SO4, right, the two H's out front, okay, are both going to be ionizable. They're going to be able to react with water to make the H3O plus ion. All right, so those are the two main characteristics of strong acids. They completely ionize in water, so they don't have any intact molecules anymore. And they are strong electrolytes. They can conduct electricity very well. Well, and then we get to the other side of the spectrum, which are weak acids. They do not completely ionize in solution. Okay, and so they are going to have some intact molecules left over. So if we take a look. Here's some examples. HF, that's fluoric acid, and we have acetic acid and formic acid and sulfurous acid and carbonic acid. All right, so these guys are what we call weak acids because they don't completely fall apart in water. In fact, if you take a look down here at this picture, we can see that there are still some intact molecules when they dissolve in water. All right, so that means it's a weak acid. They don't all completely fall apart like we saw previously. Now, to indicate that, we use a double arrow. So we see here this double arrow is going to represent that some of the molecules are going to ionize and make the H3O plus ions and the F ions, for example, for fluoric acid, hydrofluoric acid, I should say. And but, however, we are still going to have hydrofluoric acid molecules still intact in that solution as well. So we indicate that with a double arrow, meaning partial ionization. Now, just like strong acids were strong electrolytes, weak acids are weak electrolytes. They are poor conductors of electricity. They contain a few charged particles, like we saw here. Okay, so there's a few charged particles in this solution, like we see here, but it's not enough to like completely brightly light up the light bulb. So we're going to get a very dim light bulb if it's a weak electrolyte. All right, so how do we know if it's going to be a strong or a weak acid? Well, it's going to depend on the attraction between the anion of the acid and the hydrogen ion, the ionizable proton within the molecule. And so this has a lot to do with electronegativity, okay, and attraction for each other. And so if the attraction between hydrogen ions and the anion, okay, so that just means the other part of the molecule. So this A with a minus is the anion part of the acid. So like, for example, if it's HCl, the anion, okay, would be the Cl minus. Okay, so if the attraction between the hydrogen ion and the anion is weak, all right, that means water is able to break it apart, and it's going to be a strong acid. It's going to be able to completely ionize in water, where all we get is completely broken apart ions in solution. All right, so that's if the attractions between the positive and the negative parts of the acid are weak. Now, if the attraction is strong, okay, so think about it. If H and A have a very strong attraction to each other, water is not going to break them apart, okay? So water can't break them apart, or it can break very few apart, so we're going to get intact molecules here in this solution. And so we're going to call that a weak acid, okay, because there's going to be a few that gets broken apart, but for the most part, their attraction is very strong. They don't let anybody in, including water. So this we would call a weak acid. So it has to do with the attraction between the hydrogen ion and the anion of the acid. All right, so when we're talking about strong and weak acids, okay, we can determine the hydrogen ion or the hydronium ion concentration in the solution just by basically characterizing it as a strong or weak acid. So, for example, if it asks you to determine the H3O plus concentration in each solution, well, if we have 1.5 molar of HCl, HCl, like we've seen previously, is a strong acid. So HCl is going to completely dissociate in water, right, to make this. And so if it's completely dissociating, that means we are going to end up with, if we start out with 1.5 molar of the entire molecule, okay, we are going to end up with 1.5 molar H3O plus as well, okay, because they're completely going to break apart. Now that is in contrast to this acid, acetic acid. Acetic acid was on our list of weak acids. And so what we can say is that what happens is that the molecule is not going to completely break apart. We're going to get, some intact molecule as well. So we'll have some H3O plus, okay, with the anion over here. I'll just put A minus because I'm running out of room. But we do have some intact, molecules. And so our concentration is not going to be, exactly what we started with. So what we'll say is that the hydronium or hydrogen ion concentration is going to be less than 3.0 molarity. Okay? We can't say exactly how much it's going to be. It might be different at different time periods when we test it, but we know that it's not going to completely fall apart. So that means that we are not going to have 3 molar hydronium ions. All right, last one is this 2 molarity nitric acid. Nitric acid is a strong acid. It was listed under our strong acid ones. So that means that nitric acid, when we react it with water, is going to completely fall apart into the ions. Okay, hydronium ion, H3O plus, and a nitrate ion. And so if it completely falls apart, that means that whatever concentration we start with is the concentration we end with. So our concentration of H3O plus is going to equal what we start with, 2.5 molarity. Okay, so what you're going to do now is you try it. Okay, so first off, go back and look at our lists of strong acids versus weak acids. And what you're going to do is, if it's a weak acid, then the hydrogen ion concentration is going to be less than the molarity you start with. If it's a strong acid, we know it's going to fully fall apart, and so our so it's less than. And then if it's a strong acid, it's going to completely fall apart, and it's going to be equal to our first, what we started with. So take a moment and take a look at these. You can pause the video and try them for yourself. Help each other out, whatever you need. Okay, strong bases work just like strong acids. A strong base is going to completely dissociate in solution. Okay, so it's going to completely break apart to give off their OH minus ions and leave the cation behind. So here's some examples of strong bases. All right, we've got lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, and barium hydroxide. Right, we can see that they all have their OH behind them. So a good indicator of a strong base is going to be OH actually in the formula. So these are what we call, remember, Arrhenius bases, where when we put them in water, they're going to completely dissociate to make this hydroxide ion. So a strong base, just like a strong acid, we're going to get no intact, base solution or base molecules. So NaOH, for example, is going to completely dissociate into Na plus and OH minus. We're going to get no NaOH that are still intact. And so, like we had mentioned earlier, for example, if we have a 1.0 molarity NaOH solution, right, and it completely dissociates, that means we have a hydroxide ion solution of 1 molar, and our sodium ion solution is going to be 1 molarity. Now, a weak base, okay, just like a weak acid, does not completely ionize or dissociate, and it produces hydroxide ions by accepting a proton from water, therefore ionizing water to form OH. So basically it's breaking apart a water molecule and taking a hydrogen for itself, so that all that's left over of the water molecule is this OH ion. Okay, so weak acids, for the most part, are going to do that, versus weak bases, for the most part, do that, versus the strong bases, which actually have the hydroxide ion within the molecule. So here's some examples of weak bases. Okay, right here. Ammonia and ethylamine and methylamine and the bicarbonate ion, these guys are weak bases. And we can see that they don't have the OH, they don't have the little OH minus or OH in them themselves. Okay, so weak bases are not going to do that. So remember the way they work, these are Bronsted-Lowry, right? Bronsted-Lowry type bases are going to be weak bases versus our Arrhenius ones up here, they're going to be strong bases. So remember the way they work is they take a hydrogen, right, from water. Oh, they take a hydrogen from water to end up with an extra hydrogen. So NH3 we start with turns into NH4 because you took that extra hydrogen. So when water loses a hydrogen, what's left? Well, OH minus. Okay, so that's how that works. That's how we increase the hydroxide ion concentration in a solution with a weak base. Okay, so this is just like what we did with the acids. Okay, the strong and the weak acids, except now we're talking about bases. So determine the hydroxide ion concentration in each solution. So remember, this is just relative, not exact. So we just have to take a look and see, is it in our strong base category or a weak base category? Is it Arrhenius base or is it going to be a Bronsted-Lowry type base? So KOH is a strong base. It's our Arrhenius, so this is going to be strong. And so if it's strong, our hydroxide ion concentration is going to be equal to the molarity that we start with, because they're going to completely ionize water to make all of the OHs possible. Okay, so OH, the hydroxide ion concentration of the first one, KOH, is going to be just what we start with, 2.25 molarity. Now, this guy is methylamine, okay, is a weak base. Remember, we categorize them as a weak base. He's Bronsted-Lowry type, and which are weak. And so they are not going to completely ionize in water. We're going to have this methylamine molecule still intact sometimes. All right, and so what that means for the hydroxide ion concentration is that it's going to be less than what we start with, less than 0.35 molarity. We don't know how much less, but we know that it definitely will be less because it does not fully ionize in water. And our last but not least, we have strontium hydroxide. Look, we got that OH in there. He is a strong base. Okay, he's going to completely ionize in water, and so our hydroxide ion concentration is going to be equal to what we start with, 0.025 molarity. All right, so if it's got an OH in the molecule, it's going to be strong base. If it does not, if it ionizes water, instead, it's going to be a weak base. So you guys take a moment to pause the video and take a look at these yourselves and see if they fall into the weak versus strong category, and categorize, or not categorize, but determine the hydroxide ion concentration for each of these solutions. All right, so let's shift gears a little bit and talk about water. Okay, water is what we call amphoteric. It can act as either an acid or a base. And we saw this earlier in the last lecture, okay, when we were taking a look at Bronsted-Lowry acids versus bases. So we said that water can sometimes act as an acid and water can sometimes act like a base. If it acts like an acid, it gives away its proton or hydrogen. If it acts like a base, it takes the proton or the hydrogen away from it. All right, so in fact, pure water can actually go through what's called self-ionization, all right, meaning that it acts as an acid or a base with itself. So within your bottle of water sitting at your desk, if you've got one, those water molecules are ionizing themselves. They are stealing hydrogens away from another water molecule to become hydronium and hydroxide, or those hydronium and hydroxide, or the hydroxide stealing the hydrogen ion from hydronium ion to go back to water. Okay, so it's a whole hot mess up there in your water bottle, okay, that you don't even realize. It's what we call self-ionization. So if we take a look at this example here, okay, if we just kind of take A and B, the first and the second water molecule, we can see the first water molecule, if we take a look, has taken, okay, a hydrogen ion, okay, which actually means that he's the base, okay, and this water molecule, right, gave away his hydrogen ion, so he's the acid. All right, so when water does this, all right, we're going to basically be getting equal amounts, average. If we take a look at all of the water molecules in your water bottle, okay, on average, the hydronium ion concentration and the hydroxide ion concentration are going to be equal, okay? We can't have, half molecules of water or anything like that, so obviously it's all going to equal out in the end. And in pure water, the molarity of hydrogen ions versus hydroxide ions is 1 times 10 to the negative 7th molarity. That is in a neutral solution. Okay, the hydronium and the hydroxide ions are going to be equal. All right, so we call that the ion product constant for water, or Kw. Okay, this is ion product constant for water. And so for water, we've got two ions that make up water, the hydronium ion and the hydroxide ion. And in pure water, the hydronium ion is going to be 1 times 10 to the negative 7th molarity, and the hydroxide ion is going to be 1 times 10 to the negative 7th molarity. So if we multiply those two together, which is what we do for equilibrium constants, we're going to end up with 1.0 times 10 to the negative 14th molarity. All right, and this is going to be more significant a little bit later when we talk about the pH scale and how pH plus pOH is always equal to, guess what, 14. Okay, so if a neutral solution has equal concentrations of hydronium and hydroxide ions, what if we have an imbalance? All right, and so that's what we're going to take a look at. So an acidic solution is going to be one that creates more or additional hydronium ions than just the plain water that was there to begin with. Okay, so what we get is an increase of hydronium ion concentration. So the hydronium ion concentration is going to be greater than 1 times 10 to the negative 7th molarity. That's an acid solution. And please, please, please keep in mind that this is a negative 7th exponent. So when we're talking about acidic solutions, this exponent is going to be lower in number. Okay, so in an acidic solution, the exponent, okay, is like, times 10 to the negative 1 to times 10 to the negative 6. Okay, we can say. So even though we say it's greater than 1 times 10 to the negative 7th, that means the exponent is actually less than negative 7. Or the value, I should say, is 1 and to 6. All right, because remember, it's opposite when we're talking about negative numbers. Negative 1 and negative 6 are greater than negative 7 on a number line. Okay, so basic solutions are the opposite. They're going to create more or additional hydroxide ions. And so what this is going to cause is an increase in hydroxide ion concentration. And so the hydroxide ion concentration in basic solutions will be greater than 1 times 10 to the negative 7. All right, and so we can take a look at, this simple picture here says that if it is an acid, this side is acid, it's going to have more H plus ions. If it is a base, like this side, it's going to have more OH, negative ions, than regular water. And the other picture on this slide is a bunch of examples, household examples, and kind of what their acidity versus basicity is. And so we can see, though, that as we get more basic, okay, our hydroxide ion concentration is going to increase. All right, if we get more acidic, our hydroxide ion concentration is going to increase. Okay, so we can see that there. Okay, so sometimes we need to figure out the hydroxide ion concentration for a solution if we know the hydronium ion concentration for a solution. All right, and so from that we can figure out if it's an acid, base, or neutral substance. So here we're going to calculate the hydroxide ion concentration for each of the solutions to figure out what type of solution it is. Now, every time that we are doing this, we are going to use our knowledge that the ion constant for water is the H3O plus concentration times the OH minus concentration, and that's going to equal, right, 1.0 times 10 to the negative 14. Okay, so we're going to use that kind of as our equation. So let's take a look at the first one. If the hydronium ion concentration is 7.5 times 10 to the negative fifth molarity, what's the hydroxide ion concentration? Well, let's plug our numbers into this equation. So we're going to do 7.5 times 10 to the negative fifth times our, this is our x basically, equals 1.0 times 10 to the negative 14. Right, so to get our little x by itself, we're going to divide both sides by 7.5 times 10 to the negative fifth. And when we do that on our calculator, we'll get 1.3 times 10 to the negative 10 molarity. Okay, and remember, this is our OH ion concentration. So the exponent negative 10 is super small. So if our hydroxide ion concentration is very small, that means we have a lot more hydronium or hydrogen ion concentrations. So in this case, this solution here is acidic, because our hydroxide ion concentration is super small compared to our hydronium ion concentration, which is 10 to the negative fifth, which is greater than 10 to the negative 10. All right, so let's take a look at another one. Here we have hydronium ion concentration of 1.5 times 10 to the negative 9. So again, let's plug it into our original equation up here. So we go 1.5 times 10 to the negative 9 times x, okay, equals 1.0 times 10 to the negative 14. So let's divide both sides by our hydronium ion concentration. When we do that, we get 6.7 times 10 to the negative 6 molarity. Okay, remember, this is our hydroxide ion concentration. And if we look, our hydroxide ion concentration is significantly more than the original hydronium ion concentration of times 10 to the negative 9. Remember, 10 to the negative 9 is lower than 10 to the negative 6. So if our hydroxide concentration is higher than the H pluses, okay, that means it is a basic solution. Okay, so you got to do a lot of these to practice, because otherwise you just be like, wait, what? Okay, so make sure you go home and you practice this stuff. Review it, all right? You need to be studying outside of class, okay, like on a weekly basis at least, if not daily. That would be great. Okay, let's take a look at our last example. We have a hydronium ion concentration of 1 times 10 to the negative 7. If we plug that into our equation, we're going to do 1.0 times 10 to the negative 7 molarity, right? That's our concentration times X equals 1.0 times 10 to the negative 14. Okay, and so we divide both sides by 10 to the negative 7. Divide by 10 to the negative 7. We end up with 10 to the negative 7. Okay, which is exactly the same as our hydronium ion concentration before. So if they're equal, they are neutral. Okay, so this last solution is a neutral solution because the concentration of hydroxide ions is now equal to the concentration of hydronium ions. All right, and now it's time, you guessed it, for some you try it problems. Okay, so now you guys are going to do this calculations. You're going to calculate, this time though, please be aware that you are calculating the hydronium ion concentrations for these solutions. So the last time we were doing hydroxide ion, this time you're going to do hydronium ion. So they're going to give you the hydroxide ion concentrations. You solve the equation, remember, Kw equals hydroxide times hydronium equals 1 times 10 to the negative 14. Right? Use that equation to plug in the hydroxides to solve this time for the hydronium ion concentration. And then you're going to have to use your logic to figure out if the hydronium ion concentration is more, then it's an acidic solution. If the hydronium ion is less than our hydroxide ion, then it is a basic solution. All right, so take a few minutes to pause the video and work with each other to figure out whether these solutions are acidic, basic, or neutral by solving for hydronium ions. All right, so working with numbers that are like times 10 to the negative whatever concentrations is a little weird and not very handy. So what scientists have done over the years is basically developed what's called a pH scale, all right, or a pOH scale. It's basically a way to express the acidity or basicity of solutions by either concentrating on the hydrogen ion concentration of the solution or the hydroxide ion concentration of the solution. So a pH scale is going to express acidity or basicity of solutions based on the concentration of hydronium ions, okay, or remember, same thing as hydrogen ions, all right. This is the scale we use most often. You've probably heard of pH scales, pH balanced, pH, something, something. Okay, so on our pH scale, we can see a picture of it right there in the middle. 7, pH of 7 is what we call neutral. So if the pH of a solution equals 7, that means the hydrogen ion concentration is equal to the hydroxide ion concentration. Okay, and that's 7. And hey, if you remember what we just talked about just a few minutes ago, when they're equal, they're both 1.0 times 10 to the negative 7. So the 7 is, basically right there in the middle, just like the pH scale. Okay, so they're equivalent. Now, anything that is less than pH 7 is what we call acidic. Anything that is more than 7 is, you guessed it, basic. Okay, another word for basic is alkaline. Okay, so there you go. 8 to 14 is basic, 0 to 6 is acidic, right there in the middle, 7 is neutral. Now this pH scale is what we call a logarithmic scale. Basically what that means is that, remember, a logarithm is based on 10, okay? And so a change of 1 pH unit corresponds to a 10 times change in the hydronium or hydrogen ion concentration. So going from a pH of 1 to a pH of 2 is 10 times as many hydrogen ions. So for example, if we have a pH of 1, that means we've got, 100, okay, hydrogen ions, and we go to pH 2, well, it's 10 times. Okay, so we're becoming more basic going that way, so it's going to be, only 10 hydrogen ions versus 100. So it's a 10-fold increase or decrease depending on which way you're going with the scale. But any change of 1 pH unit corresponds to a 10 times change in hydrogen ion concentration. All right, so because it's a logarithmic scale, we can use an equation that uses log in order to convert our, random molarities of 7.5 times 10 to the negative 9 molarity of, hydrogen ions. We can convert that to a single kind of number on the pH scale. And so pH is going to equal the negative log of our hydrogen ion concentration. So what you do is you just simply plug into your calculator negative log of your hydronium or hydrogen ion concentration. You push equal sign and bam, it gives you the pH. So let's take a look at the first one. If we have a hydronium ion concentration, then those should say pluses, not minuses. Okay, if we have a hydronium ion concentration of 1.8 times 10 to the negative 14, all right, if we put into our calculators negative sign log, okay, and in parentheses we put 1.8 times 10 to the negative 14, close our parentheses and push equals, we're going to get pH reading of 3.74. Okay, and so what that means is this is less than 7, so this is an acidic solution. All right, it's as easy as that. Yes, there are ways to solve for logarithms without a calculator, and I'm sure you guys learned that in, like, I don't know, pre-cal maybe. All right, but we're going to use our calculators. All right, so have them handy. All right, next is... let's do the next one. pH is going to equal negative log of, this time our hydrogen ion concentration is 7.2 times 10 to the negative 9. So we put that in our calculator, we push equals, and we get 8.14. Now 8.14 is higher on the pH scale than 7, so that means it is basic. All right, so let's briefly talk about the pOH scale. Basically, it expresses acidity or basicity, but this time we are going to be basing it on the hydroxide ion concentration instead of the hydronium ion concentration. So this scale is logarithmic, just like the other one, and it works pretty much, in the same general way, except now we're talking about OH instead of H. So it's pOH versus pH scale. But our calculations are going to still be the same. pOH is going to equal the negative log of the hydroxide ion concentration. All right, so now on our pOH scale, see, this is where it gets a little confusing, okay? Because on our pH scale, anything below 7 was acidic, right? Because it had really high concentrations of hydrogen ions. In this case, in our pOH scale, if anything is below 7, it is basic, because now we've got a lot of hydroxide ions, which makes things basic. And if anything is on our pOH scale is greater than 7, it is acidic, because the hydroxide ion concentration is very low. Okay, so we got to keep those kind of in mind, because it can get confusing. All right, so here, though, is something we need to keep in mind. is that the sum of pH plus pOH of a solution is always equal to 14. Because remember, just like we saw with our kW of water, okay, concentration of hydronium ions to hydroxide ions always ended up being 1 times 10 to the negative 14. Okay, well, this 14 is coincidentally right there. So if we have our pH plus our pOH, it's going to equal 14. Okay, so we can keep that in mind. So we can easily convert from pH to pOH by just doing 14 minus the other. Okay, and we get our pH or pOH. All right, here's an example of a particular problem that is going to require the inverse log. How fun is this? Okay, the inverse log of our pOH. So it says calculate, instead of, so before we had our hydroxide or hydronium ion concentrations, and then we solved for pH or pOH. Well, now here we're given our pOH, and we have to figure out what the concentration or the molarity of our hydroxide ion is. And so basically we just take the inverse. So you can just, in your calculators, push inverse log, right, of negative 8.55 and push equals. And what you'll get is 2.8 times 10 to the negative 9 molarity. All right, or the math for this is actually a lot easier. You could also do, basically, if you take the pOH and you put it, times 10 to the negative value of that, all right, then you'll end up with the same answer, 2.8 times 10 to the negative 9 molarity. Okay, either way, just do the inverse, just do opposite, okay, on your calculator. So instead of pushing negative log, you push negative inverse log. So please be sure you make sure that you find that button on your calculator, and if you don't, either ask somebody around you who may have found it, or you can ask me at a later time. All right, we have come to our final topic for this lecture, which is buffers. Solutions that resist pH change. Dun, dun, dun. Okay, so a buffer is something, like I said, it's a solution that's going to resist pH change, and the way it does it is it neutralizes any added acids or added bases. Okay, and this is because a buffer solution contains a significant amount of both a weak acid and its conjugate base. So if we have a weak acid and a conjugate base, and we add a base, then the weak acid that's in there can neutralize it. Okay, or if we add an acid, the conjugate base can neutralize the acid. All right, so that's kind of what we see here in this bottom picture. So here we've got a buffer solution. Okay, and if we add HCl to it, okay, what's going to happen is that this buffer solution, the conjugate base, these little guys right here, okay, which are bicarbonate solution or bicarbonate little pieces, are going to be able to neutralize the HCl by breaking it apart and holding on to the hydrogen. Okay, so we can see that over here. If we hook up, so on the right side, if we hook up this blue piece with half of the H half of the hydrochloric acid, all right, we can see that they come together, right, and neutralize it. Okay, and the opposite would be true if we added a base. Okay, then the acid could neutralize the base. Okay, and so a really good example of a buffer system is actually in our blood. Our blood uses carbonic acid and carbonate okay, as its conjugate base, right, in order to keep our blood pH between 7.36 and 7.40. It's very precise in pH. Plus, if you think about it, going, from just a change in 1 unit would be a 10-time fold change in hydrogen ion concentration. So we want to make sure that we keep our bodies, at a specific pH range that's very tight. And so just kind of an FYI, if your blood pH drops below 7, okay, if it gets too acidic below 7, or if it gets above 7.8, too basic, then death results. Dun, dun, dun. All right, so let's see how this buffer system works. So in a simple buffer system, for example, we can mix the solutions of acetic acid and its conjugate base, sodium acetate. See how they share the same anion part, right? C2H3O2, C2H3O2. Remember, one just has the ionizable proton in front that makes it an acid, right? And the other one is going to be able to grab, if it breaks apart, it's going to be able to grab that acid, therefore it serves as a base. So if we add more base to this solution, what's going to happen, so for example, if we add NaOH, which is a base, to the solution, the acetic acid part of the buffer system is going to neutralize the base. All right, and so we can see that NaOH is going to be broken apart, and the OH, the H here in the acetic acid is going to give away its H to this OH to make water. All right, and then we're going to get Na hooking up with acetate from the acid part of the molecule to make sodium acetate. All right, so this base is going to neutralize, or is going to be neutralized by the acid to make water and sodium acetate. Okay, now if we add more acid, what happens? Okay, so if we add HCl to the solution, we've got a bunch of sodium acetate base. This base is going to take away this H, okay, as bases do, all right, to make, in this case, a weaker acid. Okay, it's still an acid, yes. You're like, well, how does that neutralize it? But it's a weaker acid, okay? This acid does not nearly dissociate in water, so it's not going to be giving off its hydrogen ion as much, because remember, acetic acid was a weak acid. And then also we get a higher concentration of salt, okay, which neither is an acid nor a base. All right, so if we add more acid to it, the conjugate base is going to neutralize the acid. So that's how this buffer system works. So as long as we don't add more base or more acid than the concentration that we have in our simple buffer system, then it's going to be able to resist our pH change very well. All right, we've come to our last slide in our lecture, and what this is a practical example, I guess, of acid base and how buffering systems kind of work, or actually in this case go awry, in our bodies. So ethylene glycol poisoning. Remember, ethylene glycol we talked about in the very beginning of the chapter is found in antifreeze, right, which we use in our cars to keep from our engines freezing up, okay, with it basically, remember, it is a boiling point elevator, which means that it's going to increase the boiling point of water, and then remember also it decreases the melting point of water. So if we add antifreeze to our engines, the engines won't freeze. Whatever water is inside will freeze at a very much lower temperature than 0. All right, so we can protect our engines that way. All right, but however, a lot of times, I guess, dogs and cats and whatnot can, lick this up. If we've got a leak in our, in our engine or whatever, and this stuff is leaking out, and they drink a lot of it, they can actually get poisoned, because what happens is that this gets into their system, and it's basically like an alcohol. All right, so the first stage is, the animal, and this actually can happen in humans too. The animal kind of acts a little drunk, all right, and the liver is going to start kicking in and metabolizing this, all right, and as it metabolizes this, it metabolizes it into glycolic acid, all right, which, kind of then our body just it can't use, so it goes into our blood, and this glycolic acid enters our blood, and if too much of it enters our blood, it's going to overcome our buffer system. So a little bit, no problem. We got a buffer system in our blood to neutralize it. But if the dog, cat, or human drinks too much, and we get too much of this glycolic acid in our blood, then it's going to basically drop or plummet our blood pH. And so what happens is that your body basically is trying to hyperventilate. Okay, so you're going to be breathing really hard, all right, hyperventilating, because that's one way that your body can also get rid of, extra basic stuff is through carbon dioxide release. Okay, and so if this happens and they can't get, enough carbon dioxide out, then, they die. Okay, basically, end result is death. Antifreeze kills. All right. However, if you know that your dog, cat, or human has drinking antifreeze and they've looked drunk and whatever, and it's because of antifreeze, what you can do is actually, and this is the ironic part, give them more alcohol. But in this time, it's ethyl alcohol, like what's found in alcoholic beverages. All right. Now, the reason why this works is interesting and simple. Ethyl alcohol and ethylene glycol is metabolized in your liver by the same enzyme. So if you bombard that same enzyme with ethyl alcohol now, which it actually it's preferable, it prefers ethyl alcohol to ethylene glycol. So what happens is this ethyl alcohol is now going to start sticking to the enzymes and being processed by these enzymes more. So this leaves the ethylene glycol, okay, kind of just in your system, and it's not being broken down. And if it's not being broken down, all right, then that's, it's better than if it was turned into this horrible acid that makes your pH drop in your blood. So leaves ethylene glycol untouched in your body, and what your body does is just filter it through the kidneys and out your urine. Okay, and so it's kind of weird. That if you have ethylene glycol poisoning, and this actually works with methylene as well, okay, or methanol, which is a type of alcohol that is not the consumable kind, then you can treat it with ethyl alcohol, okay, or just alcoholic beverages. So I guess that's one good reason for alcoholic beverages. All right, not that that gives you permission to go out and get drunk to protect you from antifreeze or anything like that. That makes no sense. But it's just kind of a little FYI if you've, seen your dog or cat, kind of looking all stupery, drunk and whatever, you can assume that it may be antifreeze poisoning. And so, on your way over to your vet, you can, give them some alcohol, and maybe it'll help save their lives. All right, that is it. We are done with this lecture. And so with that, we have closed another chapter in our study of chemistry this semester. And so please make sure you take the time to re-go over these lecture notes, get this stuff in your head, practice, do those syllabus, back of the textbook practice problems as much as you can, as often as you can, to keep it in your head for the final.